Today I want to talk to you about the history of atomic theory and subatomic particles. So to begin with, we've discussed the atom a little bit already. It's the smallest identifiable unit of an element. What do we mean by that? We mean if you have one single atom of carbon, you know the element is carbon. Let's say you have half of a carbon atom. What does that even mean? But could you then tell that it was carbon? No. Okay. These elements can't be broken down into simpler substances. So that's what led to the original term of atom, which literally meant indivisible, as Democritus suggested, is that the atom is the smallest portion of an element that you can have and still have that element. Okay? If you have half of a carbon atom, guess what? You don't have carbon. You don't even have really half of a carbon atom. Okay? You have other simpler substances. So since then, we have found that you can split the atom, you can divide it. Okay? But the original term is still good because of the fact that the atom is directly related with the element it corresponds to. So why can't we see atoms? We can see lots of things that are small, but we can't actually see atoms. If you think about the bacteria that's pictured here, what is happening, why you can see bacteria under a light microscope is because even though they're small, they're not so small that they can't interact with light. Light is around the wavelength of around 400 to 700 nanometers, whereas a bacterium is normally around the size of a micrometer. So it is huge in comparison to the wavelength of light. But an atom is normally 10 to the minus 10 meters, so it is much smaller than the 400 to 700 nanometers that light corresponds with, the wavelength of light. Okay? So because of that, anytime you have a photon of light, it's going to essentially pass through, pass over, pass around the light, but it's not going to interact with it. And so since what we're looking at when we're looking at light is reflections and absorbances, we can't see the light, we can't see the particle because we're not getting any reflection from them. Okay? So in order to see atoms, they have to actually probe them with something that's smaller than the wavelength of visible light, such as electrons or something similar. Okay? But that's the reason we can't actually see them. So when we're looking at the idea of what composes an atom, there are kind of a couple different ways, different models that people have come up with, physical and conceptual models. The conceptual model is what we're going to be talking about today. It contains three main parts: the electron, the proton, and the neutron. The idea that these subatomic particles compose an atom, and it's because of them that we understand a little bit more about its charges, its space, how it works. Okay? The planetary model, it's a little limited in its predictions, but it's been updated since then to include shells, which we'll talk about at a later point. Okay? But that's basically going to go a little bit further to look at the predictions of where electrons actually exist in the atom. Today we're just going to be talking about how an electron exists outside of the nucleus. Okay? And now these models are excellent guides, but they are limited. And so basically what we're looking at in this course is going to be just the basic models. But just wanted to make you aware of the fact that these models are simplistic and that scientists everywhere around the globe have made much better updates to these models that are much better predictions of the true properties of the atom. But this is a great fundamental place to start. All right, so to begin with, Ben Franklin. What do you think? Fact or fiction? You really think Ben Franklin went for a walk in a lightning storm? He decided he wanted to fly his kite in the lightning storm, and then boom, he got struck by lightning? Okay, to be honest, it's fiction. I think Ben Franklin was eccentric enough that it makes for a really good story, but truth be told, he didn't actually go walking in a lightning storm with a kite. But it makes a great story, okay? But what he actually helped lead us to is understanding the charge buildup that exists in an electric storm. So for instance, whenever you have lightning, you've got a negative charge that builds up in the sky, okay, up in the clouds, and then you have a positive charge that builds up on the ground, on Earth. Whenever you have lightning, those positive and negative charges, because opposites attract, they want to equilibrate so quickly that you get this giant shock, this giant just transfer of those two charges together that helps equalize the charges. And so that's what we're seeing is with lightning, okay? And so Ben Franklin helped think about the fact that there were positive and negative charges in the atmosphere, at least, that could help lead us to understanding the atom. Okay? The electron was the first subatomic particle discovered. Scientists realized that electricity could pass through glass tubes as glowing rays, okay? Both with or without gas in the tube. So the idea here is you see those no vacancy or vacancy sign. That's basically a tube that's got gas passing through it. The cathode ray tube is what you see in figure B, okay? And with that CRT tube, it's cathode ray tube. That's the thing that existed originally in those really old monitors. They were called CRT monitors because they stood for cathode ray tube, okay? So the idea was, is inside that tube, if you've got a vacuum inside of it, no atoms are present, you somehow still are able to transfer charge. How is that possible? We know that if you put a wire between, two different entities, let's say you hook up a battery and you put a wire across it, if you apply a little resistance to it, throw a light bulb in there, you can light the light bulb, okay? The wire serves as a conductor to pass electrons from one atom to another throughout the wire. But if on the inside of a tube there are no atoms that can help facilitate that charge transfer, how in the world are you allowed to have electrons moving from one side to the other? That's what they wondered too. They were able to see its deflection, they were able to see its acceleration, they were able to see the fluorescence that happened due to the excitation of these electrons. But they didn't know that electrons existed. So that's what kind of helped them propose that maybe there is this negative charge or just this charge that is a distinct difference than the whole atom itself. Because there are no atoms present, but you're still able to shoot a charge across, maybe there's something called an electron, which is different from the atom, or even better yet, part of the atom. All right, so from there, J.J. Thomson proposed what's called the plum pudding model. I don't know if you guys have ever eaten a fruitcake before. Not very good in my opinion. That's what you see in the bottom left-hand corner. It's like a cake that's got raisins and other fruit items just dispersed randomly throughout the cake. The cake would be perfect if they just covered it in chocolate and they'd be happy, okay? But, a lot of people really like these fruit cakes. This plum pudding was what they ate back in the olden days, okay, and so that's what they compared it to. And it was basically this mass globular substance with random chunks throughout it. And so J.J. Thomson proposed this model and said, hey, this must be how the atom works. The atom is no longer indivisible because it's this sphere of positive charges with these electrons just present all throughout it, okay? The idea was he used these cathode ray tubes and he looked at them to measure the angle of deflection of the electrons. And so what he noticed is if he increased the charge of if the charge of the particle was increased, the mass of the particle was also increased, then that was proportional to your angle of deflection. So as you increase the mass of the particle, you would change your angle of deflection. As you increased or decreased the charge of your particle, that angle of your deflection would also change. And so he noted that there had to be a distinct relationship between the charge of the particle and the angle of deflection, which led him to the theory that electrons and something that was positive existed within the electron. So he still didn't know about protons. He just instead surmised that, oh, there's something negatively charged inside this atom. Let's call them electrons, and let's disperse them throughout a positive sphere. Why did he need the positive sphere? He knew he was just shooting the electrons through the cathode ray tube. But he knew if you were going to have a whole bunch of negative charges close together, why would that be bad? Negative charges repel each other. So if you put too many of them close together, they're just going to repel each other and they're not going to stick together in a form that's helpful to us in the form of an atom. So he surmised that there must be this positive globular cake portion of the atom that was positive to hold all the electrons in place and help neutralize them. Okay? So J.J. Thomson came up with this idea that there must be electrons. All right, Robert Millikan kind of went further on J.J. Thomson's experiments. He proposed the charge of an atom. What he did was he had these two charged plates that were parallel to each other. He then used a mist of oil droplets to inject them into the chamber. They fall because of gravity, okay? Now the force on the oil droplets is due to their mass, okay? Force equals mass times acceleration. You don't need to worry about that, but just what's important to note there is that the mass is directly proportional to its force. Okay, so he knew the force that should be on the oil droplets because he knew the mass of the oil droplets. But what he didn't know is what its charge was. So what he was able to do was he was able to adjust that electric field until the droplet essentially hovered. And he knew that that hovering then was the negative charge was balancing out was repelling the negative charge of the oil droplet. The charge plate was helping it to, the positively charged plate was helping to help it hover, okay? And he knew that that force of the electric repulsion was canceling out the downward force of gravity. And so he was able to exactly figure out the charge of an electron. He knew it was negative, but he didn't know how much it was, okay? Additionally to that, he realized that no matter what he injected into the chamber, there were always multiples of a certain charge, meaning, let's say the charge was 5. He would always only see charges of 5, 10, 15, 20, 25, okay? So he thought, oh, well, every electron must have this exact charge, but if you've got multiple electrons in an atom, then you have multiple charges, which makes a lot of sense, okay? So Robert Millikan came up with the idea that there must be a charge of an electron, and he was able to figure out what that number was. All right, so the electron, at this point now, particles were found in cathode ray tubes. They're the fundamental unit of all atoms, so the idea is that they exist inside of all of atoms. They exist in negative charge. They have a very small mass, which is 9.1 times 10 to the minus 31 kilograms, and that mass was calculated from Millikan's experiments where he knew the charge of the cathode particle, okay, which is 1.60 times 10 to the minus 19 coulombs. And so basically that was the particle charge that he was able to determine from his oil drop experiments, and it let him not only the charge of the electron, but the mass of that electron. Through this, you're able to determine many physical and chemical properties of atoms. So with the idea that there is electron exists, scientists were already realizing that this helps them figure out so many things about different atoms that they didn't know before. They were able to help categorize them further. All right, but we want to keep going because that's not the only subatomic particle that's important. Rutherford was the next scientist. He was the one that came up with the gold foil experiment. So how this experiment worked is they took a really thin gold foil and they laid it in the middle of this detector that you see wrapping around here. Then they took lead, which is our source of alpha particles. An alpha particle is composed of basically a helium nucleus. It has 2 protons and 2 neutrons. They take it and they can shoot it at the gold foil. What they expected to see was it to just pass right through the gold foil and just hit the other side. But that's actually not what happened. Okay? The way he compared it is he said it's like you fired a 15-inch shell at a sheet of tissue paper and it came back and hit you. So imagine someone holding up a Kleenex from 15 feet away from you, you shooting a gun at their Kleenex, and instead of it passing through like you would expect, it instead bounces off that Kleenex, comes back, and hits you in the face. How surprised would you be? That is exactly how surprised Rutherford was. All right. So he had to then come up with a theory that matched this, because the idea is you've got this, basically, if you've got this plum pudding model that you see in the top left-hand corner, the reason the alpha particle should have passed through them was because compared to the size of an electron, an alpha particle is huge. So it should just pass right through the Kleenex, okay? Electrons are so small compared to an alpha particle, it's like comparing the Kleenex size to your shell, the shot that you shot at it, okay? So all of it should have passed through and hit the other side, but instead it wasn't. So he thought maybe there's something to that gold foil, that it's not just electrons submerged in this positive goo, okay? So that made him develop the nuclear theory of an atom. And the nuclear theory of an atom just basically says there has to be a small region of dense matter that the alpha particles can interact with, okay? And that dense matter region is called the nucleus. So in that bottom left-hand corner, we now have the nuclear model, which is still used today. The idea is the nucleus is in the center of that sphere. So instead of having a positively charged sphere with electrons kind of scattered throughout, you have a positively charged nucleus that resides inside the center of that nuclear model. And then the electrons still go around the nucleus, but you no longer just simply have the positive charges, spread out. Okay? That makes a lot more sense, because now whenever you shoot it at it, if you've got gold nucleus, which is much bigger than an alpha particle nucleus, basically, you're going to have that alpha particle, whenever it hits that nucleus, it can bounce right back. It can also bounce to the side and be scattered. And so Rutherford was able to correlate his findings from that experiment and help determine, oh, there's got to be a nucleus. And so he was able to propose this nuclear model from his experiments. All right, so this is kind of on the right-hand side. You kind of see the gold foil, which is approximately what they're showing here. They try to get as thin as they could. So if you had a 3-atom thick foil, then the idea was that most of the alpha particles should go to the other side, but the fact was he was still seeing a substantial number of them be deflected or re-reflected. Okay, and so that's how he was able to come up with this idea of a nuclear model. Okay, so proposing this nuclear model, he came up with kind of 3 main tenets. The first, 99% of an atom's mass and all of its positive charge are contained in a core nucleus. So 99.99% of all of the atom's mass is in the nucleus. Okay, what about those electrons? What? I thought they were mass. They had a mass. They do, but it's just so small compared to the mass of a nucleus that it's insignificant. So 99.99% of an atom's mass is in the nucleus, and that nucleus is positively charged. Okay? Number 2, most of the atom's volume is empty space through which negatively charged electrons are dispersed. So the idea is, what's most of the atom? It is actually empty space. So if, for instance, I were to tell you, hey, well, this desk I'm staring at, it's mainly empty space. You might look at me like I'm crazy, but really, I would actually be right, okay? The idea is that even though you've got all these little atoms that are so close together, they're close together, but within their kind of sphere that they take up, most of it's empty space, okay? And those negatively charges of your electrons are dispersed throughout that empty space. Negatively charged electrons are equal in number to positively charged protons in order to make a neutral atom. Okay? So he incorporated the idea in his nuclear theory that if the positively charged nucleus equals the charge on the electrons but opposite, it's neutral atom. So that means for every 1 positively charged proton you must have 1 negatively charged electron. Okay? And that's how a neutral atom remained. Okay? Now, there are still a lot of questions after this. For instance, okay, we've got this nucleus and it's positively charged and it contains protons, but if you have a whole bunch of positive charges within this dense sphere, why aren't they repelling? Okay, great question. The other question was, okay, we've got all these negatively charged electrons flying around outside the nucleus and all these positively charged protons, why aren't they just attracted to each other? Why don't they just join and turn back into that plum pudding model? Okay, so there are still a lot of questions remaining to be answered at this point. All right, let's look at a black hole. That's what this is a picture of. A black hole. I don't know if anybody knows a lot about black holes in here, but black holes come from is what they think is the death of a star. That basically a star can implode on itself and basically shrink down and become so dense that everything is attracted to it. Okay? What I mean by that is if all of the atom is empty space, most of the atom is empty space, what's going to happen if you get rid of all that empty space? You can make it so dense that you essentially have neutron nucleuses like right on top of each other. That's almost kind of what happens in a black hole. It's just this extremely dense object in the center of space where everything for, light years away is attracted to it. Everything can feel the pull of that gravitational field from that extremely dense star that exploded. Okay? In fact, it's such a strong gravitational field that scientists have come up with the term spaghettification, which I don't know if anybody's heard of that, but that's kind of the idea that if you were to travel to a black hole, that if, let's say you're flying Superman style toward the black hole, that your fingers would feel the pull of gravity before your arm would, and so that your fingers essentially start to get pulled. You'd turn into a spaghetti before you ever got there. And so that's one of the ways that we don't have of traveling to a black hole, because it's so dangerous. You'd essentially have your spaceship torn apart before you ever got to the center. Now we can study them by looking at light and looking at the effects of gravity, but still, it's quite an interesting phenomenon, and a lot of that's looking at just simply the kinetics and the forces that are present within an atom. All right, so that was the question. If atoms are mostly empty space, why don't they pass through one another? Well, if you think about it, the nucleus, positive, the electrons, negative, so they attract. But if you have electrons floating around in that outer space, most of the volume of an atom, then as one atom comes close to another atom, those electrons can repel. Okay? They can repel each other because positive charges repel positive charges and negative charges repel negative charges. Okay. Could the nucleus then be composed entirely of protons? So that was the question we proposed earlier. And James Chadwick had that exact same question. What he did was he looked at radiation signatures and noted that the radiation was not the same as what was produced by either electrons or protons. Now his work is not in our textbook, so if you want to learn more about him, you'll have to resort to good old Google. Okay? But basically he was the one that proposed the existence of a neutron. He tried to answer the question of, well, if you have multiple positively charges pushed really close in a dense mass that is the nucleus, why don't they repel each other? This neutron is the other component of the nucleus that basically gets in between your protons and helps balance out those positively charges so that way they don't just straight up repel each other. The way it does is it's got this thing called nuclear force. A nuclear force is sort of like a glue, a cement that kind of holds those protons in strong. So even if they're repelling each other via their similar positive charges, that glue is going to hold them in regardless of how much they're repelling and struggling to get out. So it's basically the neutron helps overcome the positively charged repulsion that is felt within the nucleus. Okay? So James Chadwick helped propose the existence of the neutron. All right, so this is kind of a summary slide. So the three particles, subatomic particles that exist within the nucleus, within the atom, are the electron, the proton, and the neutron. The proton and the neutron exist within the nucleus. The electron has a negative charge, the proton has a positive charge. The neutron has no charge. The electron has a really small mass compared to the proton and the neutron, so much so that it's almost insignificant. Okay? So kind of think through these things and just think about them over and over again so that you can almost say without thinking, what is the majority of the atom? Ah, empty space. Where's most of the mass located? Ah, the nucleus. Why is the mass located in the nucleus? Oh, it's because it's composed of protons and neutrons, and each proton and each neutron is about 2,000 times more than the electron. Good, okay? Which one's positive? Which one's negative? Which one's neutral? Just kind of think about all these things, because all of these things will really help the original scientist think through and come up with this idea of nuclear theory. All right, so those are the questions we just discussed. What subatomic particles are in an atom? What makes up most of the mass of an atom? Go ahead and take a minute and just pause the video if you need to and write down your answers, just to kind of test yourself and see how you're doing. So what subatomic particles are in an atom? I hope you said protons, neutrons, and electrons. What makes up most of the mass of an atom? Your answer can be two. It can either be nucleus or it can be the nucleus, which is contained of protons and neutrons. Okay? All right, let's look at our periodic table. The periodic table, remember, was put together by Mendeleev, and so he originally was the one that first started ordering the periodic table, but since then we have learned so much from it, and this periodic table will be your friend, your best friend, in fact, for the rest of this course. Okay? So first off, let's look at beryllium as an example. So remember before, we have Be, which is your element symbol, okay, your chemical symbol, and then you have beryllium, which is your chemical name, okay? Additionally now, we have two things we want to focus on, our atomic mass, okay? So remember, what does most of your mass of an atom come from? Your nucleus. So it comes from your protons and your neutrons, okay? Your atomic number is the other thing we want to focus on, and that is Z. It's given the symbol Z. Now that number always, always, always stands for the number of protons. Okay? If you ever change the number of protons that an atom has, guess what? You just changed the element. Meaning, to go from 19 protons to 20 protons, you change from potassium to calcium. To go from 20 to 21, you change from calcium to scandium. Okay? So anytime I give you a set of protons, if I say, what is the element with 8? Actually, we'll go with 26 since it's on the slide. With 26 protons, you can immediately tell me, oh, it has to be iron, because iron is the only one with an atomic number of 26. Okay? Really focus on that atomic number, because that is going to be so important whenever it's a neutral element. Okay? So the number of protons, you can figure that out by looking at the atomic number Z. Okay? So now something I wanted to mention is If it's neutral, this number is also the number of electrons in an atom. Because remember, we said in order for it to be neutral, the positive charges have to balance with the negative charges. So if your atomic number is 4, and it's a neutral atom, you have 4 protons, and that means you also have 4 electrons. Okay? So it's always the number of protons in an atom, and it's also the number of electrons if it's neutral. If it's not neutral, we'll be talking about that at a later point, then those two numbers are not one and the same. Okay? But if it's neutral, then that number is equal to the number of protons and the number of electrons. Okay, so kind of to review, make sure at the end of this lecture you can name the 3 subatomic particles and list their charge. Make sure you know what number on the periodic table tells us the number of protons in an atom or in an element. Also make sure you know that if an atom is neutral, how are the number of protons related to the number of electrons in an atom? Okay, so that goes back to the previous charges. If you need to stop here and think about these further, please do, because it's really important that you understand how to look at a periodic table and figure out the number of subatomic particles that exist for that atom. Okay, we're going to practice this here in a second, but before you go further, think through this and really consider what is going on the periodic table. Okay. So let's practice. At the bottom part of this screen, I pulled each of the little cubes off of the periodic table so that we could look at each one of them separately. Okay? So for instance, let's look at oxygen. In each one of these columns, I've written atomic mass, atomic number, number of protons, number of neutrons, and number of electrons. All right, so we're going to practice and just define each one of these for each of these elements. Okay? So the first thing is atomic mass. I want us to just go ahead and approximate the mass number. So instead of just writing out 16.00 or 24.31, we want to approximate it, okay? And we'll kind of discuss where the atomic mass comes later in more detail. But for right now, the approximate mass is good enough for us, okay? So for oxygen, first thing it asks for is atomic mass. So we go to our periodic table, and we find our atomic mass, which I circled there. So the atomic mass for oxygen is 16. Okay, and next asks for our atomic number, which remember our symbol for that was Z. Okay, and sometimes I'll abbreviate each of the other ones as a P for proton, an N for neutron, and an E with a minus sign for electrons. Okay, so our atomic number for oxygen, remember we find that right above the chemical symbol, so it is 8. And the number of protons, remember, is always, always, always equal to our atomic number. So if you ever have a different number for atomic number versus protons, it's wrong. Atomic number is always equal to the number of protons. Okay? Then we have neutrons. Okay? Remember what we said before about the atomic mass? The atomic mass comes from which 2 subatomic particles? Protons and neutrons. So if our mass is 16 and we have 8 protons, how many neutrons do we have? 16 minus 8 equals 8. Okay? Another way of saying that is atomic mass equals our number of protons plus our number of neutrons. So these 2 categories right here should always add up to atomic mass. Okay? Then the last column, number of electrons. We're assuming all of these are neutral. Okay, that was given to us in the prompt. These are all neutral elements. So if it's neutral, then that means your positive charges have to be equal to your negative charges. So for this example, your protons will always be equal to your number of electrons. So if you have 8 protons, you have 8 electrons. Okay? What I want you to do is I want you to pause the video right now. Okay? What that will do is allow you to finish out this graph. Then come back to it and I'll help you solve it and you can double check your work. Okay? But this is very important that you understand how subatomic particles can be identified from the periodic table. Okay? So pause your video right now. All right, welcome back. Hopefully you've paused it and unpaused it and you've already got all these answers down. So we'll just work through them all. Okay? All right, first of all, we'll do all of the atomic masses. All right, those are all of our atomic masses. So for magnesium, we'll approximate that to 24. Copper, you should have gotten 64. We'll round that up to 64. Gold, 197. Helium, 4. Neon, 20. Okay? The atomic number, that's our top number, remember? Our atomic number for copper is 29. Our atomic number for gold is 79. Our atomic number for helium, well, I almost wrote helium, is 2. Our atomic number for neon is 10. Okay? Practice with your real periodic table instead of just the numbers that are written below here, because it's always helpful to kind of get used to figuring out where atoms exist on the periodic table. Okay? So remember, our atomic number is always equal to our number of protons. We can fill in our number of protons next to it. Okay, and those are the same. Okay? I'm going to go ahead and jump to number of electrons because that's easy. We've got a neutral element. So if it's neutral, our positive charges have to balance out with our electrons. So that means for every one proton, you need one electron. So we can just recopy this table over. Okay? Good. So now we've got our atomic number, our protons, our atomic mass, and our number of electrons. What remains is our number of neutrons. So remember, our protons plus our neutrons need to add up to our atomic mass. So here, for magnesium, our mass is 24. We have 12 protons, which means we have 12 neutrons. Okay? For copper, we have 64 is our atomic mass, minus 29 gives us 35 neutrons. Okay? Gold is 197 minus 79 leaves us with 118 neutrons. Helium is 4 minus 2 gives us 2 neutrons. Neon of 20, 20 minus 10 gives us 10 neutrons. Notice, as our atoms get much bigger, so looking at copper and gold, you're going to need a lot more neutrons in order to hold those positive charges together. So what you'll find is as the atom gets bigger and bigger, you really do end up increasing your neutrons even more than you end up increasing your protons. And that's perfectly fine. With the bottom, with the lower numbers, your protons and your neutrons are going to be a lot more similar. Okay? Those are just general periodic trends that exist. Okay? All right, so that's when you're thinking about subatomic particles. That's how the theory helps us figure out how to correctly identify the number of protons, neutrons, and electrons for every element, basically, just by looking at the periodic table. All right, so kind of to recap for today. The atom is composed of protons, neutrons, and electrons. The protons and neutrons are in the nucleus and compose most of the mass of the atom. The electrons are outside of the nucleus and compose most of the volume of the atom. Most of the atom is empty space. The periodic table is used to find the number of subatomic particles of every single element. Okay? Specifically, we looked at today neutral elements. Okay? So make sure you completely understand this lesson before going on further. I can't say that enough.